All right, I did check the answer during the quiz here. Again, we were doing this integral with a 9 there. We did this substitution. Ultimately, through a bunch of algebra, we got to that integral, and we simplified to that. And I know it's hard to see here with all these words. Final answer in simplest form was 3/4 plus ln of 5/29 to the 5/32 power. That is the same as this, even though it does look a bit different. 3/4 minus the 5/32 can go in that power. The minus sign there is not saying that plus sign there is wrong. The fact that I wrote 5/29 here and mathematically wrote 29/5, the reciprocal, means these are actually the same number. So I did do it right. Quickly, let's look at these other two problems, but we'll have mathematically do the integrals. Flow rate, just like the tank that I showed you in the first class, first half of the lecture. If a flow rate of water entering the tank is given by this, here water is just entering, not exiting. So we only have an inflow, not an outflow. That is a function giving you the gallons per minute as a function of time that the water is going in. That function is decreasing, so water is coming in fairly fast at time 0, in fact 10 gallons per minute, because e to the 0 is 1. But that's an exponential decay. The graph of this function goes down, which means the water's not coming in as fast as over time. The inflow is slowing down. The water level itself is still going up, but the flow rate, the inflow, is decreasing. Find the total amount of water that enters the tank during the first 20 minutes. This is really a derivative. I didn't write it that way. There's no prime here. But it is the derivative of some function, in fact, the function that represents the volume. To find the change in the volume, maybe R is the volume or V is the volume. The derivative of V is little r of t. To find the change in the volume, how much enters the tank in this case, because it is only an inflow, you would integrate r of t. From 0 to 10. To do that integral by hand would be a substitution. You could let W equal negative 0.2t.
Would it be 0 to 20 since it's substitution?
Thank you. 0 to 20 minutes. First 20 minutes. Okay, let's have Mathematica actually do the integral. Okay. Integrate from 0 to 20 this function tan e to the negative 0.2t. This will be the volume, the change in volume, which is how much enters the tank. About 49 gallons. The area under that, the graph of little r of t, from 0 to 20, the area is going to be about 49. And that represents the amount of water that enters the tank. We could do the average flow rate too, or we could find the average flow rate because we could take that integral and divide it by the length of the interval, 20. I told you that percent sign refers to the previous output, right? Last time. Take that and divide it by 20, which is the length of the interval, and that would be the average flow rate. So on average, over the entire 20 minutes, the water is flowing at 2.45 gallons per minute. It starts out at 10 gallons per minute, decreases to, at time 20, what would it be? 10 times e to the negative 0.2 times 20, decreases to about 0.18 gallons per minute. The average flow rate is 2.45 gallons per minute. It is a It's a decreasing function, but it's concave up. So in a sense, it spends most of its time in low values. So the average flow rate should be closer to the lowest value than it is to the highest value of 10. This one here is kind of abstract, no numbers. Assuming the height of an object is h0 at time 0, that's the starts at h0, that's the initial height, and its downward velocity is given by that equation. Now, when would a downward velocity be given in like an equation like that? Actually, most of the time. Things are not as ideal as in physics, where you talk about the acceleration due to gravity being the only force, and therefore the acceleration of the object is constant. That's not the case. There's air resistance. And in certain situations, perhaps for a rock or a ball, for a leaf that would be, or a feather, that would be real extreme. I'm not sure that that's the best model for that. This does end up being a pretty good model for the velocity. It is the downward velocity. Since the height measures an upward position, we would actually have to integrate the negative of this. Does that make sense? Since the height is an upward position, excuse me, yeah, the height is a upward measuring kind of thing. Above ground is positive. And the velocity is a downward velocity. The height is going to be the negative of the integral of the velocity, or the integral of the negative velocity, either way. That integral with an appropriate constant of integration to make the height at time 0, h0 will be the answer. Plus c just can't be just anything. Integrating 1 is going to give you t. The mg over k just stays there with a negative sign. This is one of the terms in the height function. What about integrating this part? E to the negative k t over m. A bit tricky. To try to do it right, you might want to do a substitution. Maybe over to the side even. Let w equal negative kt over m. dw is going to be negative k over m dt. Bunch of letters, but it's only ultimately h and t that are the variables. M is the mass. G is the acceleration due to gravity. K is some constant that probably depends on the object. Is it a feather or a rock? Integral of e to the w. dt is going to be negative m over k dw. So you get negative m over k e to the w plus c when you do that indefinite integral there. W is that. If I have not made a mistake, it looks like we have plus, no, excuse me, ultimately a minus. That minus and that minus make a plus. But we got a minus there. So it is actually ultimately a minus. Minus m over k e to the negative kt over m plus c. But since we want to know the height function specifically based on the fact that we're assuming it starts at height h0 at time 0, we need to set this equal to h0 when t is 0. When t is 0, what does this become? It becomes 0 minus m over k, e to the 0 is 1. That must equal or plus c, that must equal h0. So in fact, the c must be h0 plus m over k. It's something specific, not an arbitrary constant. If I want the initial height to be h0, that means at time 0 I want this entire thing to equal h0. Plug in t equals 0 there to get 0, here to get minus m over k. Don't forget about the plus c. Set that equal to h0 and solve for c. It looks like this is c. So the final answer would be then to take this and plug it back into there, and that would be the form of your final answer once you do that. This is actually one of your homework problems. Try to do it from scratch without looking at your notes. Why does this work? Why does substitution work? And in particular, today I want to just address why does this changing the limits of integration when you change variables, why is it the thing to do? Question?
Wait, so this was a substitution problem and not an integration by parts problem?
Right. Even though it's under that, yeah.
Oh.
Sorry, it's just, it was a blank space. Sorry to confuse you. Why does substitution work? And in particular, focusing on why does it work with the definite integrals to change the limits of integration. When you do a substitution problem, let's go back to the very first example we did. I think it was this. First example in lecture 8 on Wednesday. We let w equal x squared plus 4. dw was 2x dx. And this became the integral of w to the 10th dw. We got w to the 11th over 11 plus c, and then we replaced it in terms of x. This is an indefinite integral, but what I want you to notice here is if I make some function definitions, if I let f of x be x to the 10th power, and g of x be x squared plus 4, if I do that, that implies the original integral, 2x times x squared plus 4 to the 10th power, can be thought of as the integral of f of g of x times g prime of x. You see how that works? If f of x is x to the 10th and g of x is x squared plus 4, since f prime of x, or since g prime of x, excuse me, is 2x, the 2x is the g prime of x, and the x squared plus 4 to the 10th power, that's f of g of x. Plug in g into f, and you get x squared plus 4 to the 10th power. That's the kind of expression you get when you use the chain rule to differentiate a function of the following form. Capital F of g of x, where capital F is an antiderivative of little f. Think about the chain rule. You've got an outside function up here, an inside function. Capital F is the outside, little g is the inside. The chain rule says take the derivative of the outside, plug in the inside, and multiply times the derivative of the inside. But if capital F is an antiderivative of little f, I can also write that like this. So I get a match. What is capital F in this example? It's x to the 11th over 11 plus c, but you don't have to put a plus c, it's going to turn out. When you integrate it with this thing with respect to w, you really get capital F of w. I'm telling you all that to show you, to make more sense out of the equation I'm about to write. Suppose capital F prime of x is little f of x for all x in the interval between a and b. Then the integral of little f of g of x times g prime of x as x goes from a to b is the same as the integral of little f of w as w goes from g of a to g of b. You might wonder why I have the capital F in here. The capital F is going to help me explain why these are equal. I am assuming, of course, in looking at this equation, that g is differentiable everywhere. And really, it works nicest when f is continuous to prove this. That is what we did when we did this as a definite integral. If I decided to put limits of integration here, for example, 2 and 3, if I decide to make it a definite integral, we change the limits of integration using this equation here, w equals x squared plus 4. The new limits would be 2 squared plus 4 is 8, and 3 squared plus 4 is 13. In this example, the equality of these two definite integrals matches what I have circled over there. A is 2, b is 3. Little f and little g are the same functions that you see here. The new limits for the new integral in terms of w, g of a is 8. When you plug in 2, a equals 2 into this equation, x squared plus 4, you get 8. 13 is g of b. b is 3. When you plug in 3 into this equation, you get 3 squared plus 4, which is 13. This is the key equation you want to prove to verify that you can do that kind of thing for this example. How would you prove this? It's the fundamental theorem of calculus. Why are these two things equal? Well, here's where the capital F comes into play. Focus first on this one. The fundamental theorem of calculus would say if you want to integrate this little f over this interval, find an antiderivative of little f. We already know one is capital F. And plug in those limits for integration and subtract. This is capital F of g of b minus capital F of g of a. To show these two things are equal that are in blue, I have to show this is also equal to that. But that also follows from the fundamental theorem of calculus and the chain rule, what I have written up here. The function you're integrating in this integral is this function here, little f of g of x times g prime of x. Its antiderivative, or one of its antiderivatives, is capital F of g of x. So once again, the fundamental theorem of calculus would say, to integrate this, evaluate its antiderivative at the upper limit endpoint minus the value at the lower limit of integration. The upper one is b, the lower one is a, and lo and behold, these are the same thing. These are equal. That's an equal sign, not an 11. I know that was hard to follow. Abstract math, by its very nature, is often very hard to follow. It's something you got to keep working at. I think it would be worthwhile to go through this again, maybe not today, because we have another thing to do today, to help you see the connection. You can't just listen to me once and think you're going to get it. Okay? It's something you got to kind of rethink about. I would encourage you to think of about it on your own. The key abstract equations are this one, based on the assumption that capital F is an antiderivative of little f, and the fundamental theorem of calculus applied to both of these integrals to see that you get the same thing, and therefore these integrals are the same. It justifies what we did here. But it's hard to see how the abstract equations relate to more down-to-earth equations without making these identifications. That's helpful. You want to think about it in terms of examples. I would encourage you to think about it after class or tomorrow or something. Maybe next time we'll try to go over it again. Okay? Do you have to know it for the test? Possibly. It's possible. I'm not really doing a full proof here because I'm not writing it in sentences. Proofs are arguments and should be written in sentences. I'm trying to help you see the main idea, and that's probably good enough for us. So if this were on the test, I'd probably write out some things in sentences and maybe leave blanks for you to fill in. Might be a way to emphasize the meaning of what's going on without having you have the burden of trying to explain it completely. I want you to see the key ideas with some help. Okay? But we'll go over this again maybe next time, next Wednesday. So do think about it in between. All right, we're going to end class the last 7 minutes here with a couple integration by parts examples. And you do have some homework problems where you're going to use integration by parts. Typical kind of integration by parts problem is something of the form, say, integrate x times cosine of x. If you think about that kind of thing, it's not clear that a substitution would be the way to go, because what would you let w equal? X? You wouldn't get anything different. Should w equal cosine x? Then dw would be negative sine x dx, where there's no signs in there. It's definitely not clear that substitution would work. Integration by parts is what you want to do. Without explanation, let me just tell you what to do because we're short on time. You create, you look at this integrand here, and you break it down into a product of two things, one of which you're going to call u, and the other of which you're going to call v prime, at least in our book's notation. Okay? Some books, you find something called dv first. Our book uses a v prime. We do have a product of two things. So one of these things, x, and the other thing, cosine of x, are going to be what we define u and v prime to be. Which should be which? That's the key question. Which should be u and which should be v prime? Well, this is not a foolproof guidance here, but oftentimes you want to let u be something whose derivative is simple. Not always, oftentimes. If you let u equal x, its derivative is simpler. U prime is 1. The derivative of u with respect to x. If you do it in terms of du, you'd say du is 1 dx. But our book uses this notation. That's not something that always is the best thing to do. I will show you examples where it's not the best thing to do, maybe even today if you're still. V prime must be the other thing, cosine of x. If you had let u be cosine of x, u prime would have been negative sine x, which is not any simpler. You also, as a general rule, want v prime to be something that's not too hard to integrate. And in fact, yes, that's the case here. We can integrate cosine of x to get sine x. Do you need a plus c? Actually, you don't. This is an indefinite integral, so we're going to tack on a plus c at the very end. But we don't need one in our intermediate steps. The formula for integration by parts says the answer is u times v minus the integral of v times u prime. With respect to x, there would be a dx in there when you plug your function in. But in sort of sloppy notation, It's u times v, those are both functions of x, minus the integral of v times u prime as functions of x. And when you do that integral, it is with respect to x. I didn't put a dx in there. We read it sloppily at first, at least that's what our book does. What's u and v? U is x, v is sine x, so I get x times sine x, minus the integral of v times u prime, sine x times 1. We aren't done yet, there's still an integral there, but it's an easier integral to do. Just do it like that, we're almost done. X sine x minus the integral of sine, which is negative cosine. So we get minus a minus, which is really a plus. Now tack on your plus c at the end. Does this work? Is this the answer? You should check it. d dx, take the derivative of that with respect to x. You need the product rule. And it turns out integration by parts is the reverse of the product rule, just like substitution is the reverse of the chain rule. We need the chain rule for substitution. Integration by parts is the reverse process of the product rule. And we need the product rule when we check it. Take the derivative of x sine x by first taking the derivative of x and multiplying it times sine x, plus x times the derivative of sine x, which is cosine x. For that second part, you don't need the product rule. The derivative of cosine is negative sine. The derivative of c is 0. Don't need to worry about that. The sine of x and the negative sine of x, that is a sine here, cancel, leaving you with the original integrand x cosine x. It worked. In 2 minutes, I'm going to do a trickier example. Integrate x arctan of x. Why is this tricky? It's because that advice that I gave you of letting u be something where u prime is simpler is not a good idea. And the reason it's not a good idea is because if you let u equal x so that u prime is 1, v prime would have to be arctangent of x, which means v would be what? What's the integral of arctangent? You don't know that. You do know the integral of 1 over 1 plus x squared is arctangent, but you don't know the integral of arctangent itself. It can be found, but you don't know it. It's not a memorized thing. So in fact, it's better to let u equal the arctangent of x in this case. We're still going to get a slightly tricky integral when we do it. Let v prime be x. I guess you can still say u prime is simpler. 1 over 1 plus x squared is simpler than arctangent of x, perhaps. But v prime, the benefit here is definitely easy to integrate. 1/2 x squared. You don't need to add the plus c here now, you add it at the end. The formula, again, says to do this, you take u times v as functions of x and subtract the integral of v times u prime as functions of x, and you do it dx with respect to x. uv is 1/2 x squared arctangent of x minus the integral of v times u prime, product of these two things. The 1/2 can come out in front. We have x squared over 1 plus x squared. That integral is a little tricky. Do this one with a substitution. Let w equal, actually I'm not sure offhand what the best thing to do is. Oh no, I know, excuse me. I know what to do, but it's tricky. The best way to do this integral is to do first long division. Take x squared divided by 1 plus x squared. And write the answer as a quotient plus a remainder over 1 plus x squared. We don't have time for that. I will say it's possible. But we don't have time for today. You have a slightly simpler example. Your example in the homework, you have a 1 there instead of an x. You want to let v prime be 1 in your example. It's a 1 there instead of x for your problem. That's it. See you.